Good afternoon. The topic of this session is enhanced vulnerability hunting in WDM drivers using symbolic execution and Taint analysis. I'm Zeze, a Team T5 security researcher and a member of TSJ and TWN48 CTF teams. I'm currently researching on the topic of Windows kernel and have presented in different conferences. It is the overview of the talk. I will introduce the WDM driver and IOCT lens proposed by us to detect the vulnerabilities in WDM drivers. We will dive into the design of IOCT lens, and I will share some vulnerability types and the real-world cases that are hunted by IOCT lens. IOCT lens have made some enhancements to get better performance, and it is evaluated with both known and unknown drivers. Let's introduce the WDM driver and IOCT lens. WDM drivers have been provided by Microsoft since Windows 2000. WDM stands for Windows Driver Model. It is used to support for devices. Currently, WDM drivers account for the most of the Windows kernel drivers in the market. There are many vulnerabilities that are found in WDM drivers and exploited by attacker or abused by malware. The steps to create a WDM driver is as following. First, it creates a device using IO_create_device. Then it creates a symbolic link for the device by calling IO_create_symbolic_link. Next, the developers for the WDM drivers can define dispatch routines for each IRP. For example, IRP_mj_create and IRP_mj_close. The most we will focus on is the IRP_mj_device control. The developers can implement IOCTL handler for IRP_mj_device control to execute different functions based on the value of the IO control code. IRP stands for IO request packet. It is a data structure to communicate between drivers and operating system. A user mode process can send IRP by calling Windows API. For example, it can call create file to send IRP_mj_create, or call close handle to send IRP_mj_close. This talk, we will focus on IRP_mj_device control by calling device IO control. So let's talk about IOCTL. Stands for device input and output control. It is an interface to communicate with the device driver. A user mode process can call device IO control to send IRP_mj_device control to the kernel mode driver with the parameters IO control code, input buffer length, output buffer, and output buffer length. The developers can execute functions based on these parameters. BYOVD attack stands for Bring Your Own Vulnerable Driver attack. This type of attack, a malware can use a vulnerable driver and load it and exploit the vulnerability in the driver to gain the privilege of kernel execution. For example, Blackbyte abuses RT-Core driver whose rewrite controllable address to bypass antivirus and execute ransomware. Candiru can abuse HW driver whose map physical memory vulnerability to install rootkit and execute spyware. Unfortunately, there are many vulnerabilities in WDM drivers that are abused in the wild. Symbolic execution is a technique commonly used in software security. We can use it to analyze code without running it on a real system. We can also use it to explore all possible paths. To know how to reach to a place of a program, we can create a mathematical model and assign symbolic variables. Taint analysis is also a commonly used technique in software security. We can use it to track potentially unsafe inputs and mark data originated from an untrusted source to identify where the tainted data may be used in an unintended way to detect the vulnerabilities. There are 3 contributions that are made by IOCT Lens. First, it enhances the ability to detect various vulnerability types in WDM drivers. Then, it can efficiently identify vulnerabilities without running it on a real system. As a result, there are 117 vulnerabilities in 26 unique drivers that are hunted by IOCT Lens, resulting in the assignment of 41 CVE. The related work of IOCT Lens includes fuzzing, like IOCTL fuzzer and IOCTL BF. This type of research is relatively simple. However, it is hard to analyze the code in depth. The second type of vulnerability of related work is fuzzing and symbolic execution, like cap fuzz and smart fuzz. This type of research does very well. However, they require the environment to analyze because of fuzzing. And the third type of related work is symbolic execution and taint analysis, like screwdrivers and popcorn. This type of research suffers from path explosion and currently few vulnerability types. So IOCT Lens enhance the vulnerability types and optimize to get better performance. Let's dive into the design of IOCT Lens. This is the diagram of design of IOCT Lens. At first, a driver is input into IOCT Lens. In the procedure of information gathering, it verifies whether it is a WDM driver by checking the presence of IO-create device in the import table. Then it fetches device name by searching a string signature. Next, it gets information such as OP codes, function addresses in direct jump by parsing the driver file. In the procedure of preprocess, IOCT Lens hooks OP codes, hooks functions, sets breakpoints to detect vulnerabilities and improve performance. It also uses techniques to customize the options to overcome different issues case by case. It also initializes structures to bypass some checks set by a program. In the procedure of finding IOCTL handler, IOCT Lens inspects the memory write event on driver object because the IOCTL handler is written into driver object. In the procedure of hunting vulnerabilities, there are 9 vulnerabilities that are targeted by IOCT Lens. Once IOCT Lens finds a vulnerability, it reports the vulnerability type, the vulnerability addresses, the parameters, the return address, and constraints. Let's share some vulnerability types and real-world cases that are found by IOCT Lens. There are 9 types of vulnerabilities that are targeted by IOCT Lens. The first type of vulnerability is map physical memory. IOCT Lens hooks mmap IO space and mmap IO space EX and see if the physical address or number of bytes are tainted, or which mean are controllable, which may lead to elevation of privilege, because an attacker can exploit the vulnerability to map an arbitrary physical address. Another situation for physical memory is that IOCT lens hooks GW map view of section and see if the section handle is controllable or it is physical memory, and the base address or commit size and field size are controllable. If the conditions are satisfied, it may lead to elevation of privilege. Take a CV in my driver 64 from driver Genius, hunted by IOCT lens, for example. In the specified IO control code, the program calls a function, which I name it arbitrary write PA. In the function, we can see that the number of bytes is tainted, and the program then calls mmap IO space with the both parameter, physical address, and number of bytes controllable. So an attacker can exploit the vulnerability to write into the arbitrary physical address. The second type of vulnerability is controllable process handle. IOCT lens hooks GW open process and see if the attributes in object attributes is not OBJ force access check, and the process ID in client ID is tainted and then passed into the GW open process. If the conditions are satisfied, it may lead to broken access control because an attacker can exploit the vulnerability to return an arbitrary process handle. Another situation for controllable process handle is that IOCT lens hooks OP open object by pointer and see if the process ID passed into PS lookup process by process ID is controllable, and the returned E process is then passed to OP open object by pointer, and the handle attributes is not OBJ force access check. If the conditions are satisfied, it may lead to broken access control. Take a CV in FIL DDS from Twister antivirus hunted by IOCT lens, for example. In the specified IO control code, the program calls a function, which I name it terminate process. In the function, we can see that the process ID in client ID is tainted by our input buffer, and the attributes in object attributes is not OBJ force access check. Then the program calls GW open process with the object attributes that is tainted. And last, the program calls GW terminate process to terminate a process handle that is returned by GW open process. So an attacker can terminate arbitrary process by exploiting the vulnerability. The third type of vulnerability is buffer overflow. IOCT lens hooks memory copy and see if the third parameter, size, is controllable. If it is, it may lead to denial of service of elevation of privilege because an attacker can exploit the vulnerability to copy any length from source address to the destination address. Take a CV in IMF Camera Protect from IOBit malware fighter hunted by IOCT lens, for example. In the specified IO control code, we can see that the program calls memory copy with the third parameter, size, controllable, and the destination address is on the stack. So it is a stack overflow. An attacker can exploit the vulnerability to gain the system privilege. The fourth type of vulnerability is null pointer dereference. IOCT lens tracks the tainted buffer and see if the program doesn't validate the tainted buffer. Because an attacker can control the input buffer to null pointer by setting the input buffer length and output buffer length to 0. So it may lead to denial of service. Another situation for null pointer dereference is that IOCT-lens hooks the kernel APIs related to allocating memory. If the program doesn't validate the return value of these APIs, it may lead to denial of service because the return value is potentially controlled by an attacker. Take a CVE in IMF registry filter from IO-bit malware fighter hunted by IOCT-lens, for example. In the specified IO control code, we can see that the program reads from our input buffer without validating the pointer. The fifth type of vulnerability is rewrite controllable address. IOCT-lens tracks the tainted buffer and see if the address to read from or the address to write into is controllable. If it is, it may lead to denial of service or elevation of privilege. Another situation for rewrite controllable address is that IOCT-lens hooks memory copy and see if the source address or the destination address is controllable. If it is, it also leads to denial of service or elevation of privilege. Take a CVE in AMD CPU profiler from AMD profiler hunted by IOCT-lens, for example. In the specified IO control code, we can see that the program calls a function, which I name it IOCTL get output file, with the parameters controlled by the input buffer. In the function, the program calls memory copy with the destination address controllable. So an attacker can exploit the vulnerability to gain system privilege. The sixth type of vulnerability is arbitrary shortcode execution. IOCT-lens tracks the function pointer by setting a breakpoint on code operation. If the function pointer is controllable, it may lead to arbitrary kernel code execution because an attacker can hijack the instruction pointer. Take a CVE in PGO driver from Visual Studio 2022, hunted by IOCT-lens, for example. In the specified IO control code, the program calls a function, which I name it IOCTL 156002. In the function, the program then calls another function, which I name it execute code, with the parameter IRP containing our input buffer. In the execute code function, it calls parse function because it parses our input buffer. In the parse function, the local variable code is tainted by our input buffer and then returned by the parse function to execute code. Execute code treats the return value as a function pointer and calls it, which leads to arbitrary code execution. An attacker can exploit the vulnerability to gain the system privilege. The seventh type of vulnerability is arbitrary write MSR. IOCT-lens hooks the OP codes WRMSR and see if the register and value are both controllable. If they are, it may lead to arbitrary kernel code execution because an attacker can hijack the KI system code by using write MSR. Take a CVE in WISE HD Info 64 from WISE System Monitor hunted by IOCT-lens, for example. In the specified IO control code, the program calls a function, which I name it arbitrary write MSR. In the function, the program calls write MSR with the both parameter, register, and values controllable. So an attacker can exploit the vulnerability to execute arbitrary kernel code. The eighth type of vulnerability is arbitrary out. IOCT-lens hooks the OP code out and see if the both parameter, port and data, are controllable. If they are, it may lead to denial of service because the attacker can exploit the vulnerability to reboot the system or turn off the system. Take a CV in SE64 driver from Intech Taiwan, hunted by IOCT lens, for example. In the specified IO control code, the program calls outward with the both parameters, port and data, controllable. So an attacker can exploit the vulnerability to cause denial of service. The last type of vulnerability is dangerous file operation. IOCT lens hooks the APIs related to file operations and see if the object name is controllable and attributes in object attributes is not OBJ force access check. If the conditions are satisfied, it may lead to broken access control because an attacker can potentially control the file handle to operate on. Take a CVE in WSDK driver from Watchdog antivirus hunted by IOCT lens, for example. In the specified IO control code, the program calls a function which I name it IOCTL 80002008. In the function, we can see that the local variable Unicode string is tainted by our input buffer. And then the program calls delete file function with the tainted Unicode string as a parameter. In the function, we can see that the object name in object attributes is tainted by our input buffer. And the attributes is not OBJ force access check. Then the program calls GW delete file with the parameter object attributes tainted by our input buffer. So an attacker can exploit the vulnerability to delete arbitrary files in the system. Well done. We have finished all types of vulnerabilities. But what about the enhancement? So let's talk about the enhancement made to get better performance. There are 5 enhancements made by IOCT lens to get better performance. The first one is improving OP codes. REP is an assembly code used to repeatedly execute something. If the size indicated in a register is too large or it is a symbolic variable, it may slow down the symbolic engine or consume many memory. So IOCT lens evaluates the size for REP and set thresholds on it. Indirect jump is widely seen in WDM drivers because the developers use switch case to determine the value of IO control code. If the jump address of indirect jump is a symbolic variable, the state in symbolic engine will be killed because it doesn't know where to jump. So IOCT lens evaluates the target address of indirect jumps and set constraints on the states, then insert the states into symbolic engine. The same concept also applies for code operation. IOCT lens evaluates the symbolic function address and set constraints on the symbolic function address, then inserts the states into the symbolic engine. Memory set and memory are widely used in WDM drivers. However, they are not the function that are imported. Instead, they are the functions that are implemented so complicated. So IOCT lens hooks them to optimize these functions to get better performance. There are some APIs that are used to set constraints on input buffer. For example, is address valid is a kernel API used to validate a buffer is valid for read or write. Proper read is a kernel API used to validate a buffer is located in user mode and is readable. On the other hand, proper write is an API used to validate a buffer is located in user mode and writable. IOCT Lens hooks these APIs to reduce the false positive because the input buffer maybe are constrained. Some APIs are used to check the current environment. Some programs use this API to check the environment and determine whether to keep executing. So IOCT Lens hooks this type of API like PS get version and RTL get version and set a symbolic variable to the output value to bypass the conditions set by the program. The same concept also applies for get system routing address and FLT get routing address. The WDM drivers can use it to retrieve the routine to call. If the return routine is not a valid function pointer, which may make the program stop executing. So IOCT Lens hooks get system routing address and FLT get routing address and resolve the routine name and return a simple procedure for these APIs to reduce the false negative. IOCT Lens implements some optional customization to overcome case-by-case issues. For example, it set the length limit to stop all states in the Symbolic engine. Or we can set loop bound to ignore the concrete loops encountered in a program. Not only set total timeout to the whole Symbolic execution, we can also set IO control code timeout for an IO control code. We can avoid the recursion state, which may slow down our Symbolic execution. We can symbolize the data section to bypass some checks made by a program, because some programs use global variables as the conditions. Okay, let's talk about the evaluation with both known driver and unknown drivers. We obtain the vulnerable WDM drivers from FISMEM drivers and drivers binaries. There are totally 104 unique vulnerable drivers, and the largest one is 1.3 MB, the smallest one is 10.1 KB, and the average size is 64.4 KB, 62.4 KB. Under the situation, for 30 minutes total timeout and 40 seconds IO control code timeout, there are 103 drivers can be analyzed successfully by IOCT Lens. The other one requires symbolizing data section to find IOCTL handler. The table shows that the number of vulnerabilities. The column of ground truth means the vulnerabilities that are manually reversed by us, and the experiment is the vulnerabilities that are reported by IOCT Lens. Obviously, there are some false negative. However, by setting the optional customization more precisely, we can reduce the false negative a lot. For unknown driver, we obtain drivers by manually downloading various software online. There are totally 318 unknown drivers, and the largest one is 71.1 MB, and the smallest one is 7.2 KB. The average size is 630 KB. Under the same situation as the non-vulnerable driver, there are 259 drivers that can be successfully analyzed. And the left 59 drivers have to be manually tuned by setting options. As a result, there are 117 unknown vulnerabilities in 26 unique drivers hunted by IOCT lens, resulting in the assignment of 41 CVE. These are the CVEs that are hunted by IOCT lens, including 4 from Microsoft and 5 from AMD. Once IOCT lens finds a vulnerability, we still have to manually investigate into the driver to write a proof of concept to report to the vendors. However, some situations may make the vulnerabilities not important. For example, it is wrapped inside the tribe except, or there may be some indirect check validating our input buffer. Sometimes the vulnerabilities have to be accessed by administrator or even by kernel. And sometimes the vulnerability is really hard to trigger because the vulnerability is in a very deep place. And seldomly, some vendors are afraid of our reports submitted to them, or they don't care about it. Let's conclude this talk. WDM drivers. The vulnerabilities in WDM drivers are important because of their kernel-level privileges. IOCT lens targets 9 types of vulnerabilities and makes some enhancement to get better performance. As a result, IOCT lens find 117 vulnerabilities in 26 unique drivers, resulting in the assignment of 41 CVEs. It is my sharing of this talk. Thank you.